Hello, I'm Professor Steve Miller. Welcome back to Compressible Flow. Today we'll be talking about the so-called critical conditions, the idea of choking, which we talked about in the previous class of flow in isentropic regimes. Then we'll talk about particular calculations using numerical methods, which are programmed in the compressible flow calculator. This is a helpful tool to check your work, but I always encourage you to work through the equations on your own. Then we'll look at a couple of examples, which I'll discuss, and you can also try on your own. Finally, we'll discuss the particular tables that are handed out through the class website. Let's get started. First, let's introduce the critical concept, if you will, of the critical conditions. Critical conditions are those where the flow accelerates or deaccelerates to the transonic condition, which is Mach equals 1. Stagnation in total conditions, as you recall, are those where we isentropically bring the flow to rest, the thermodynamic values in particular, for example, P naught, rho naught, and T naught. Critical conditions are those where we accelerate or deaccelerate the flow to the transonic condition. Imagine we have a flow at Mach 0.5. If we accelerate it isentropically to Mach 1, then we would achieve a critical condition. If we have a Mach 2 flow and we deaccelerate it to Mach 1, isentropically, then we would have, of course, a critical condition. We will require another particular stagnation condition in this class, and that's the stagnation speed of sound. We'll look at this just before, of course, we look at the conditions of critical. Here in equation 236, I show from the energy equation and the speed of sound, the particular stagnation speed of sound, where we isentropically reduce the speed of flow to, of course, C naught squared with gamma minus 1 in the denominators. So on the left-hand side, at some particular flow on a stream tube, the fluid parcel deaccelerates to Mach number 0, a zero velocity, and we achieve a stagnation speed of sound. You might think and wonder what happens to C. Should it go up or down as we deaccelerate the flow to, of course, Mach number 0? Of course, you might imagine that from the equation, the right-hand side must equate to the left. The kinetic energy in u squared over 2 is transferred into the speed of sound term, which must increase to balance the equation. Therefore, as temperature goes up, the stagnation temperature, C naught squared, must also go up through the stagnation condition. Now let's try and accelerate or deaccelerate our flows to Mach 1, and we'll denote the critical conditions with a soup star term. Recall our analysis of T naught over T goes as a function of Mach number and gamma in, of course, isentropic flows. If we invert that term and set m equals 1 for the transonic condition, which corresponds to the critical condition, and simplify, we'll arrive at equation 237. We'll have T soup star over T naught goes as 2 over gamma plus 1. You'll note that this also corresponds from our isentropic relations which we previously derived, relating, of course, C with T in terms of speed of sound on the previous page, that we can write C soup star over C naught squared. That's the speed of sound at some point in the flow, where Mach is 1. Divided by C naught, which is the stagnation speed of sound, where the flow is isentropically accelerated or deaccelerated to 0, squared goes as T soup star over T naught. We already know the isentropic relations between temperatures, static, and total temperatures. We can use those same relations, which are only varied by the powers of gamma over gamma minus 1 and 1 over gamma minus 1. We can then immediately write from our previous analysis in 238 that P soup star over P naught and rho soup star over rho naught are related, of course, to the same term 2 over gamma plus 1, which is T soup star over T naught to the powers. And so we've derived relations that only depend on gamma of the critical condition with respect to stagnation condition. For air, these values have very standard properties which show up throughout the course. These values are T soup star over T naught is 0.833, P soup star over P naught of 0.528, and rho soup star over rho naught, that's the critical density divided by the stagnation density of 0.634. You can also do the same thing with Mach number. So remember here, we can look at what happens to our Mach number at the critical condition, or the so-called characteristic Mach number, with respect to Mach number. Let's summarize these particular equations, and you see how easy they are to find. We'll simply place unity for M2 in the static thermodynamic isentropic Mach number relations, which we previously developed. Here, then, we'll find T sup star over T goes as the same quantity for all equations in the slide deck, 241 to 244, of 2 over gamma plus 1 plus gamma minus 1 over gamma plus 1 to the m squared. Once again, the powers are the same for each respective term. Gamma over gamma minus 1 for pressures, 1 over gamma minus 1 for densities, and 1/2 power for C sup star over C. You can see that same half power is inverted in 237 for C naught over C sup star. C sup star over C. Wonderful. So we develop simple critical conditions with respect to Mach number between temperature and M, C and M, P and M, and rho and M for some particular fluid parcel on a streamline with respect to the critical condition where M equals 1 for rho star, P star, C star, T sup star. We can then reduce these further and look at the relations, of course, between M equals 0 and M equals 1 in particular isentropic flows. For example, if a transonic flow is brought to rest isentropically, we might find relations between the so-called choked flow static properties, that's where M equals 1, the flow is choked according to the Mach number area relation, and the particular stagnation condition in the flow, which is the point where the flow might be brought to rest isentropically from any other Mach number besides 1, of course. Here's these relations that are simplified from the previous sets of equations. We'll have 245 to 248 in the slide deck. There'll be a common factor of 2 over gamma plus 1 to the half gamma over gamma minus 1 and over 1 over gamma minus 1 for T, C, P, and rho respectively. The same powers as the previous sets of equation, which of course is obvious because it's a reduction. Let's turn our attention to mass flow rates at the choking or transonic condition and a variable area stream tube problem. Now the mass flow rate, m dot, can be written as a function of stagnation properties and Mach number. And so if our flow has choked, our you'll see that our mass flow rate is choked. And we want to show this through mathematical analysis. This is what we observe physically in flows, and let's try and prove it and see if our theory matches experiment. We will seek particular mass flow rates at any cross-section of a variable area stream tube. So let's use our conservation of mass equation in 249. We'll write m dot, the mass flow rate, at any particular cross-sectional area of our one-dimensional variable area stream tube will go as rho a u. I've dropped the subscripts because we are evaluating m dot rho a u at the particular minimum area or the choked condition or the transonic condition. This can really apply to any part of the flow, but we'll try and make assumptions so that it's at the choked condition later. Please recall the ideal gas law, P equals rho RT. You see that I've substituted rho with P over RT. A comes over to the right-hand side, I've carried that over, and I've replaced U with the square root of gamma RT. How did I do that? Well, M equals U over C. Here, you can see I have M and square root of gamma RT. Therefore, U equals M square root of gamma RT. C equals the square root of gamma RT because we have a categorically perfect gas assumption, which we already made. Therefore, this is the simple substitution. You should be able to make this substitution on your own. Now, let's try and go to the next step where we try and isolate and remove properties and write this in terms of local properties and stagnation conditions. This is what we find in equation 250 in particular. We'll have m dot over p naught square root of r t naught times a to gamma half power times n plus 1 plus gamma minus 1 over 2 m squared of gamma plus 1 over 2 minus 2 gamma. How did we do this? We simply replaced our static relations with those of total relations with respect to Mach number and gamma of the previous analysis. And that's all we've really done. Then we simplify the equation. You can try this out for yourself, and it's a homework problem. We can simplify this equation even more in 251. You'll see, which I boxed, that the mass flow rate, m dot, will be only a function of gamma and Mach number. I've moved T naught, P naught, and A, the cross-sectional area, to the left-hand side. So you see m dot T naught to the half over P naught A is only a function of gamma and Mach number. You can see this arrangement through equation 250 by simply moving P naught and T naught and other those constant factors to the left-hand side. Now you see this particular function is formulated only in terms of gamma and Mach number. You'll see that almost everything we do in this class will be formulated in a particular way as functions of gamma and Mach number. This is why Mach number is such an important non-dimensional number in fluid dynamics. Please recall also that P naught and P and T naught and T are also expressed in terms of gamma and Mach number. You'll see many other functions in this class coming up in that form. Therefore, the charts we create in this class might often be looked at as charts of varying constant gamma with increasing Mach number for each particular gamma. And then we can find particular values of m dot in the tables. Another thing that's interesting about this particular equation 251 for the variable area stream tube with which we derived it with is that m dot will be constant in the tube, according to our current assumptions at least. T naught is constant everywhere in the tube as it's isentropic. P naught is constant everywhere in the tube because of course it's isentropic. So the total conditions are not changing. M dot's not changing. Gamma is not changing. It's constant according to our assumptions. So the only two variables that can change are m and a. Therefore, this is another interesting form which we derived and held together by the Mach number area relation. You can imagine, depending on the sign of m, as a increases or decreases, m will go up or down. We'll look at the variation of these nonlinear functions throughout the course. Let's now look at the area ratio and return to it using our newly developed tools of Mach number, mass flow rate, the critical conditions, and total conditions. This will help us understand a little bit more and make predictions of thermodynamic and fluid dynamic field variables throughout these types of flows, which are very important in aerospace engineering. We'll select a particular throat with a duct as a reference state. We'll name the area of the throat A sub T, and when it's choked, it'll be A sub star. So here in this diagram in figure 76, which I label flow through a generic converging diverging duct, which is choked. Here, the flow moves from left to right, and this ticked boundary are the solid walls, and the flow is contained with its variables inside this particular domain. Here, we'll let the Mach number be less than 1, and there's maybe some state 1 at this particular location before the throat A sub T. If the flow is choked, we can label it with a sup star, which denotes that it is, of course, a critical condition, A sup star. If the flow is choked, it'll be Mach equals 1. If we raise the pressure ratio between the front and back of this particular converging diverging duct, you'll see that, of course, Mach number remains 1 there, and we'll see why that is later in this course. A downstream location might be marked 2. We call this part of the flow, left of the throat, as the diverging portion, and the area, if the flow is after the throat and moving from left to right, as the diverging portion. We call this part of the duct where it is area decreasing before the throat as the converging part of the flow, and the part after the throat as the diverging part of the flow. Here, the Mach number goes from less than 1, it chokes at the transonic condition at the throat, which is a critical condition at m equals 1, and it accelerates again to m greater than 1. It's beautiful. And we know this can happen from, of course, our analysis in our previous classes on the Mach number area relation. Here in this case, it's a choked throw. Remember, we write A sup star. We'll call this throw area the reference area, whether or not the flow is actually sonic there, through these types of analysis. Now, through the steady flow continuity equation, that's the conservation of mass equation, which we derive for variable area stream tubes for flow through a particular duct, in this case, the mass flow rate must be the same at any cross-sectional area. For example, m dot is the same in the plenum, in the converging part, at the throat, in the diverging part of the flow, and through this exhaust area where we have a supersonic flow. M dot is constant. That means, of course, 251 applies to the whole flow, and of course 250 applies to the whole flow, and 249. These are three workhorse equations that you might be used to analyze these types of flows. Now let's take our previous equation for m dot, shown in 250, and write it in terms of A. We solve for A from 250 and we arrive at equation 252. You're welcome to try it for yourself. You'll find that A goes as m dot over a bunch of terms where gamma is the ratio of specific heat, Cp over Cv, and m is your only other variable. It's interesting now, with a substitution to get rid of T naught and P naught as their constant, of course, that this equation involves the area, mass flow rate, Mach number, and gamma. But you might wonder, how is this equation related to the reference area? We can try and define all the flow variables in this particular problem as a function of the area divided by the reference area. For example, A2 over A sup star, or A1 over A sup star, is an amazing equation that we can use to try and analyze these flows, especially when they're choked at the transonic condition. So we'll be able to write the ratio of the areas at location A relative to the area of the throat A sup star using equation 252. How do we do that? We take 252 and copy it and write A sup star and m equals 1, for instance, and take the original form of 252 and divide it by the modified form. Therefore, on the left-hand side, we'll have A over A sup star, and in the right-hand side, we'll have the reduction of the equation, and m dot cancels out because it's constant in the numerator and denominator. And simplifying with m sup star equals 1, we'll arrive at this equation. So this form, of course, is assuming that the flow is indeed choke with A sup star. This is the so-called and famous Mach number area relation. A over A sup star is now a function of gamma and Mach number, as you see in equation 253, just like we previously developed, but now it's referenced with respect to the choke condition. If we analyze equation 253, you will not be surprised that it has two particular roots, and these roots have actual physical meaning, and they correspond to subsonic flow ahead of the throat and supersonic flow downstream of the throat. For this case, shown in the diagram from figures 76 to 77, we now draw on little lines and note that the same A over A sup star produces two different Mach numbers, one which is subsonic and one which is supersonic, at equivalent area ratios A over A sup star. For example, root 1 will correspond to, say, A sub 1 over A sup star, and root 2 would correspond to A sub 2 over A sup star. A sup star remains the same in both flows. So we have completely changed this problem, and all variables in the flow, as long as the flow is choked with m equals 1 at the throat, are only a function of A over A sup star. Let's step back and make some notes on what we found, because these concepts are getting more complicated. Variations of the flow properties with Mach number and the relation to one another are important to know. The area ratio, A over A sup star, is one of the most important properties, as I've shown in this previous analysis. And if you look at the tables I've handed out with the class, all of the properties are a function of A over A sup star. But remember, there's always two potential A over A sup stars corresponding to subsonic and supersonic flow, respectively. So look at that in your tables and you'll see that we do indeed find multi-valued functions. A over A sup star, as you see, is a function only of Mach number and a particular gamma, which must be a constant according to assumptions we've made in this analysis. Therefore, the Mach number, m, is only a function of area ratio and gamma in the equations also. Remember, for Mach number less than 1, that's a subsonic flow at a particular point in the flow at least, approaching a sonic throw m equals 1, and in the opposite case, a Mach number m greater than 1, the Mach number of the flow is controlled only by the area ratio, regardless of how much power is applied to move the flow. For example, I could have an infinite pressure ratio across the device in 77, according to our analysis, and of course the Mach number in that flow would only be controlled by the area. So Mach number is invariant in this particular problem, according to our assumptions, and indeed this is what we find in practice. It is very vexing. You'll see this is a very different aspect of high-speed flow relative to basic fluid mechanics or simple and traditional aerodynamic theory. And it does indeed require some special thinking and attention, especially because it's a non-intuitive theory. Now you'll think about these equations. I hope you have the time, and the physics will become intuitive for you. We've looked and developed these equations. Now let's look at how they behave with particular graphs. This is figure 78, an important graph in the class. It is the isentropic flow properties as a function of Mach number for gamma 1.4, which might be air. Remember, gamma is the ratio of specific heat, Cp over Cv, and Mach number is the local velocity of the flow divided by the local speed of sound. Remember, in these particular flows, like in figure 77, as they move from left to right, the speed of sound is changing at every point in the flow. The velocity is changing at every point in the flow. Therefore, Mach number is changing at every point in the flow. We're not considering variable gamma flows for now. Let's try and understand this figure so you can understand what happens in the particular converging diverging duct which I've drawn in the previous figure in 77. On the x-axis, we have a log scale of Mach number. The Mach number goes from 0.1, which is rather incompressible, all the way to Mach 10. The left y-axis is non-dimensionalized plots of the static pressure divided by the total pressure, the static temperature divided by the total temperature, and the static density divided by the static density divided by the total density. It's also on a log scale from 0.001 all the way up to 1, because of course it's normalized. On the right-hand side, we have another log scale on the y-axis from 0.1 to 100. And 1 and 2, etc. are labeled for your convenience. This is the normalized velocity. Here it's v, but it could be u over u sup star, which is the velocity at the transonic condition. And of course, a over a sup star, which is the area at the throat, which is choked, denoted by the sup star or critical condition. Now we can take our isentropic equations for p over pt, t over tt, and rho over rho over rho t, and plot those because they're functions only of Mach number and gamma as developed for isentropic flows. We can also plot, now that we have them, Mach number variation with the particular temperature to get velocities over the choked velocity, and the area relation, which of course is defined by the problem's geometry. So the area is defined as this particular curve. Right? It's dependent on the particular cross-sectional area as a function of x. So a is a function of x. A over a sup star will always be 1. That's unity, and we're letting it grow before and after the choking point. Now, the dashed line on the choked or transonic or critical condition corresponds to this particular dashed line on figure 78. So I'm taking the physical problem and transforming it, of course, to the problem of the graphs. It's a transformation or mapping. So let's look at how each particular function varies. Let's first look at the area ratio. The area ratio, the area of the inlet of the converging diverging duct divided by the throat, goes as this curve here. It's plotted and defined by the geometry. As we increase the area, it rises up and goes to infinity, for the analysis at least. So the area of the exit, A2, at very large Mach numbers is very, very, very high. It's a function of Mach number, mind you. Of course, A over A sup star has a value of Mach number of 1, and of course it has a value of 1 because the A sup star over A sup star is 1. Now let's look at the pressures. The total pressure, total temperature, and total density are constant through the flow. So we're really only seeing how the pressure, temperature, and density varies, which are normalized to 1 through the flow. Up here we have P over PT. So at a very low Mach number, the pressure, of course, approaches the total pressure because it's the stagnation pressure. So that's like saying at Mach 0, PT is equal to P. That's the same for rho and T. They all have the same form, and they all decrease as you accelerate the flow. So if you take the flow and accelerate it from Mach 0 to a very high Mach number 10, of course you can see there's multiple powers of reduction in the values of pressure, temperature, and density respectively. Now let's look at the last quantity, velocity, which might be the most interesting to some people. Here's the velocity curve here. You can see at a very low Mach number, the velocity should be very small because the velocity is v in this case, and v soup star is the velocity at the throat. It accelerates because it's subsonic flow and it chokes to the Mach number 1 in the transonic or critical condition, and v over v soup star is now 1. If we accelerate the flow higher, now the velocity is higher than the reference velocity, and it approaches with, of course, at Mach 10, a value just above 2. That's v over v soup star. So don't confuse v over v soup star, of course, with Mach number, because you're taking a velocity divided by the actual velocity at the throat. However, the velocity at the throat is equal to the speed of sound. So we could also write u over c soup star if we so desired, because u soup star equals c soup star, because m equals 1 at the throat only. Once again, remember that c over c soup star will certainly vary with a function of Mach number, because c is mainly a function of temperature T, which is you can see varying. Can you try and draw the graph of where c over c soup star varies with Mach number? Let's look at some potential application of this potential theory. Here, this is a recent article from 2018 of the Russian space chief vowing to find the full name of the technician who caused the International Space Station leak. So at this time, and I'll let you read through this article on your own, you'll see that a small 2 millimeter breach was punctured in the space station. Of course, the space station does not depressurize quickly like it does in the movies. In fact, the hole through the space station represents a large high-pressure plenum flowing into a vacuum through a very small hole. The pressure ratio between the International Space Station and the vacuum of outer space is very, very large. That high pressure allows the flow to go through this little choked area. So this little area here might be, which vacuums to space, might be viewed as the throat in figure 77, where we have the condition m equals 1. It's choked flow. Therefore, according to our graph, at m equals 1, you can see that the velocity is actually a particular value. And you can find the mass flow rate out of the space station from the large plenum using the mass flow rate equations shown, say, on 251, where m equals 1, and you know the area, and you know the temperature and pressure in the space station. You then can make an estimate of how much gas, that is compressed air, in the space station is leaving on a mass flow basis, and estimate time for decompression. Take a few minutes and read the article if you desire. Let's look at a particular example together. This one reads, a gas is contained in a large vessel stored at pressure, this is static pressure, 300 kPa, and static temperature, 50 degrees Celsius. The gas is expanded isentropically through m equals 1, a choke condition, via a convergent opening. Find pressure, temperature, and velocity at the choke condition if the gas is air and helium. I'll talk about the air example, and you can try the helium example on your own through the particular solution. So the solution is, as we have expanded to Mach 1, the flow is certainly choked, and we've obtained the critical condition which we just defined in this class. We can now use our stagnation critical condition equations, which we developed, to directly find P soup star over P naught. In 254, which we developed in this class, for gamma constant gamma, which is 1.4 by definition, we have air, we'll have 2 over gamma plus 1 to the gamma over gamma minus 1. Now if we put in 1.4 for air, we'll then can find, of course, P sup star for air. Putting in our known quantities of 300 kPa, kilopascals, times 2 over 2.4 to 1.4 over 0.4, which is our values of gamma, we'll find 158.5 kPa. We now know, of course, the critical static pressure of air at the throat. We'll then do the same process for temperature. For gamma 1.4, we'll find a static choked or critical condition of static temperature for air, and we'll find from the ambient condition, converting from Celsius to Kelvin, which will be 323 Kelvin, 269.2 Kelvin. Now we need to seek velocities. Remember, our flow is choked, and it's in a critical condition. This means m equals 1. Because m equals u over c, we can solve for u and substitute m equals 1. We can calculate the speed of sound c by the square root of gamma RT, which we just calculated. This is what we're seeing in equation 260. Plugging in the values, we'll find for air 1.4 times 8314.3 divided by 28.97, that's the gas constant. Universal divided by R for air, and we'll have 2 times 269.2 Kelvin to the half power. So this is the square root of gamma RT for velocity with m equals 1, and you'll find the exhaust velocity from the plenum through the critical condition is 328.9 meters per second. You can see by only changing gamma, you can have a greatly different value, of course, for helium. Try the helium and air problems on your own for practice. Let's do another example quickly to illustrate the problems. A channel with cross-sectional area A of 50 centimeters squared carries an airflow at m equals 0.5, pressure 50 kPa, and temperature of 300 Kelvin. We're first asked to find the mass flow rate m dot through the channel. Now we ask ourselves, if this particular flow converges, what area will the Mach number reach 1.0? So we have a subsonic flow at these conditions, Mach 0.5, pressure and temperature of 50 kPa and 300 Kelvin, starting at a cross-sectional area of 50 centimeters squared. We are asked to find an area, which is no doubt smaller than 50 centimeters squared. If it's bigger, you're in trouble. Will the Mach number reach 1? We need to choke this particular flow and accelerate it through the critical condition. Finally, what will happen to the mass flow rate if the cross-sectional area is smaller than that of part B? And this is a physics question. You can show the analysis yourself to prove it mathematically, or indeed, you can just answer physically if you understand the physics by writing out a sentence. Let's try it. The first step, of course, is we'll seek m dot for the particular flow. We'll use the formula which we previously developed for mass flow rate. Go back in the video or look at your class handout to review these formulas in this class. We are then given m equals 0.5, an area of 50 centimeters squared, gamma 1.4, and R of 287 meters squared per Kelvin second squared for air. We can then directly find m dot. We can also look up in our tables or use the isentropic calculator, which I'll talk about in a second, or use the isentropic equations for P naught over P, T naught over T, and rho naught over rho for the value of Mach 0.5. This way we'll find the total conditions. You'll find for m equals 0.5, P over P naught of 0.843, T over T naught of 0.952, and of course you can find then, we don't need density, P naught and T naught of 59.3 kPa and T naught of 315 Kelvin. Since we're in isentropic flow, P naught and T naught remain constant, and so that's a very valuable thing to know. Anytime you're doing an isentropic problem, I really recommend reaching out and finding P naught, T naught, and rho naught, because you know that they'll remain constant through your entire flow field as long as you don't violate the isentropic assumption. Remember what the isentropic assumptions are. Now we know our mass flow rate from our mass flow equation and our P naught and T naught values, and we know A, and so we can use these values along with gamma to find a mass flow rate at the particular condition A of 50 centimeters squared, which will remain constant as long as we don't change the throat area. You'll find m dot is 0.504 kilograms per second. Second step, Consult the isentropic flow tables or use your equations for isentropic flow, or use the Mach number area relation, which we already found, developed in this class, for A over A sup star. At Mach 0.5, you'll see that the A over A sup star value for Mach 0.5 to find equivalent area A sup star for m equals 1 is 1.34. We then can find A sup star will be 50, because we have 50 centimeters squared over 1.34, which is the area of 37.3 centimeters squared. That's wonderful. So we found the cross-sectional area to choke the flow. The original flow at Mach 0.5 had a cross-sectional area of 50 centimeters squared. The choked area is 37.3 centimeters squared. If your area increased, you know that this, of course, is unphysical because we're in a subsonic flow, and we would deaccelerate the flow, of course, to get to this equivalent area ratio, which wouldn't make any sense. It's unphysical. So be careful of that. If you find A sup star to be larger than A in a particular problem, you know you've made a mistake. Now, part C. Let's say at this particular choke condition, or critical condition at Mach 1, the channel will carry its maximum flow rate per unit area under the given upstream conditions. If the channel is reduced to a smaller area than A sup star, two things in particular will happen. One, the mass flow rate must be reduced. Why? Because, of course, if you look at our mass flow rate equation, m dot and A are the only variables that change, and P naught and T naught are constant. Since it's an isentropic flow, P naught and T naught are constant, the mass flow rate must be reduced, especially when A is choked. So there's a mathematical reason. Can you think and describe the physical reason this is true? A second thing must happen now, since we've restricted mass flow rate, is that the Mach number upstream of the sonic condition falls below the eigenvalue of Mach 0.5. That is now, because we've changed A sup star for a given constant area at position 1 in the convergent part of the duct or stream tube, the area ratio A over A sup star will be changed, but unfortunately, the throat area will remain choked. Now that we've looked at two particular simple examples, I'll let you look at and figure out through the solution, trying on your own, a more applied example from the so-called De Laval Engineering Handbook of Flow Meters, which is a famous engineering handbook which illustrates some interesting devices to control compressible flows. Here we have a particular flow meter from the De Laval Engineering Handbook. You'll notice that there's a particular converging nozzle at this location where my cursor is moving. This nozzle is designed to choke the flow through some choked area dependent on little d. The inlet flow is capital D. These butterfly valves, of course, open and close the flow. This is a type of flow meter where you can directly and control the mass flow rate because, of course, the flow chokes at D. As we see, the mass flow rate is only dependent in this particular flow by that choked condition. Try it for yourselves in the following problem. If you have questions about this particular problem, we can talk about it in our one-on-one discussions. Now let's turn our attention to a numerical tool which is pre-programmed for you called the Compressible Aerodynamics Calculator, written by a wonderful professor, Dr. Davenport at Virginia Tech. We'll use this through this class in conjunction with the tables and equations we develop. Remember, this calculator is only a numerical implementation of the analytical equations we find in this class. I encourage you to use it to check your work as you're doing homework problems and learning the material. Here's a screenshot from the current form of the Compressible Aerodynamics Calculator. You can find it by Googling Compressible Flow Calculator, and I've also made it available through the class website. You'll see that the screenshots show particular isentropic flow relations. In fact, there's many different types of calculators on a single page. For this part of the class, you want to go to isentropic flow relations, and it's actually like a little JavaScript running in your web browser. You'll see there's a place to put gamma, which is the ratio of specific heats, and if you click and drag down Mach number, you can put in different isentropic flow quantities, such as Mach number, area ratios, total pressures, temperatures, densities, Mach numbers, Prandtl-Meyer angles, etc. And through a simple input here, say we put Mach number 1.5 and click calculate, we'll find all the relevant ratios of compressible flow and isentropic flow. That's wonderful. You can also change this drop-down menu from input to say A over A sup star supersonic to 40. For example, in this calculation, an example, you'll see gamma is changed to 1.33. They say the area ratio of a supersonic flow, that is one particular solution of the Mach number area ratio relation of A over A sup star, sup for supersonic, 40, so the area ratio is 40, gamma 1.33, they hit calculate, and they find all their properties. For example, in this particular case, you can see that 40 is mirrored in the output, and they find a particular Mach number of 5. That means with an area ratio of 40 for gamma 1.33, they have accelerated their flow from Mach 1 to 5 from, of course, the critical condition. You can try a few things and try your answers. Check your answers for your homework this way. Let's now talk about the tables of isentropic flow shown in your class handout. Here I've taken a screenshot of the first page of the tables, and you'll note that there's a number of columns. You'll note also that there's a large vertical solid line, and this is a multi-page table. This is just the first table. So this large solid line in the middle separates columns of the table. So let's look at the first one on the left first. You'll see up here, there's a gamma value of 1.4. So this table, which is basically formalized from the equations of motion using a numerical methods up to a number of decimal places, shows you all the isentropic solutions. Now, in these particular columns, the first column is Mach number, which goes from 0 all the way to 1.35 here. And you can see there's Mach number 1 right here. So here's the transonic or critical condition. This is subsonic flow in the left to Mach 0 to 1, and the lower left from Mach 1 to 1.35. The table then continues on the right of the vertical line to m equals 1.3575, all the way to Mach 2.725. And then Mach numbers increase in increasing order on the following pages. Let's look at the other columns. You'll see there's isentropic, normal shocks, PM for Prandtl-Meyer, and Rayleigh-Peto for Rayleigh-Peto tube. Let's ignore these columns labeled normal shocks, Prandtl-Meyer, and Rayleigh-Peto tube for now. You'll see there's another columns under isentropic, divided by this vertical line for P naught over P, T naught over T, rho naught over rho, C naught over C, and A over A sup star. You'll note for every Mach number, for example, there's corresponding values in the columns, and for each row, for Mach, say 0.7, we have P naught over P, T naught over T, rho naught over rho, and C naught over C. You'll note that as Mach number increases, it gets to 1, and we get values of P naught over P of 1.8929, 1.2 for temperature ratios, 1.5774 for density ratios, C naught of 1.0954 for speed of sound ratios, and A over A sup star of 1 for Mach 1. So this Mach 1 row for the isentropic columns exactly corresponds to the critical condition constants, which never change for gamma 1.4, between a stagnation flow and a critical condition flow, a transonic condition. We found those in this class. Nonetheless, as we go to supersonic conditions, you'll see that these ratios continue to increase of P naught P, T naught T, and rho naught rho. Why? Because of course P, T, and rho continue to go down along with speed of sound, increasing temperature. You'll also note that A over A sup star is always positive because A must always be greater than or equal to A sup star, the critical condition, or the transonic area. This same 6 columns continue on the right under the isentropic columns. Later in the class, we'll talk about normal shockwaves, Prandtl-Meyer, and Rayleigh-Peto. Every one of these values is found by the equations for isentropic flow, which we developed in this class. So if you're on an exam and you have the tables, you can, and you know a particular Mach number, say it's 0.5, you can quickly go to Mach 0.5 and know all your important ratios of isentropic flow through a simple table lookup. Remember, there is multi-value solution for A over A sub star. So if you're given an area ratio, say 1.01, you'll note that there's two values of 1.01 in the table, but not corresponding exactly to 1.01. So you'll have to do linear interpolation between rows of the table. If you don't like doing linear interpolation, you're always welcome to solve the particular equations themselves with your calculator or on paper if you're so inclined. In this class, we defined and derived the so-called critical conditions. And we looked at how these critical conditions are related to choking or the transonic condition of converging diverging ducts, which correspond to the minimum area of the area Mach number relation. We then looked briefly at a few examples and explained two particular numerical methods, that is tabulated use of tables or the compressible flow calculator. Thank you very much for your time. I'm Professor Steve Miller.